you have a question at any time, don't hesitate to unmute your mic or to just type it in the chat. So we finished section 7.7, and let's get into section 7.8, which deals with SN1 and E1 reactions. So here's our overview. Check this out. Consider the only reaction on this slide, this one right here, where we end up with both substitution and elimination products. In the substitution reaction, what that means is that we're substituting the bromine for an ethoxy group. And then elimination means you're losing something, right? If you lose a hydrogen and the bromine, you can end up forming an elimination product. So elimination means loss of HBr is essentially what you're losing, a hydrogen and a bromide. Anyhow, so we end up with a couple of products in this case. And you notice that this substrate is tertiary. This is a tertiary alkyl halide. And since it's tertiary, we know that SN2 can't be happening. And if we look at the reagent, the only thing we have is ethanol, just some plain old ethanol as the solvent. Therefore, the elimination cannot be the result of an E2 reaction, because for an E2 reaction, we need a strong base. And for an SN2 reaction, again, we need a primary or a methyl alkyl halide. So what's going on here? And it turns out that the formation of the substitution and the elimination products both follow first order kinetics. Remember SN2 and E2, those followed second order, but now these reactions follow first order, and that confirms that neither SN2 or E2 is recurring. And if we write the rate law for this reaction, right here, it's that rate is equal to the rate constant multiplied by the concentration of the substrate only. So we only have to look at the concentration of the substrate. That's it. First order kinetics. Well, let's take a look at this in more detail. The mechanisms of substitution and elimination in this case both start with the same step, ionization of the substrate. Put another way, they both start with the loss of the leaving group, the bromide. It just falls off. And if you're thinking, well, why can that happen? Right? That didn't happen in an SN2 or an E2. Well, it's because since we have a tertiary substrate, we end up with a tertiary carbocation. And we know that a tertiary carbocation is much more stable than a secondary, primary, or a methyl. And once we form that carbocation intermediate, it can undergo substitution by the solvent or elimination via the solvent to produce the SN1 and the E1 products respectively. Put another way, my students taught me, SN together, so you can think of E1 and SN1 at a time. The steps happen individually. The first step is the loss of leaving group, and the second step is either a nucleophilic attack or a proton transfer to form the substitution or elimination products. So depending on whether you get substitution or elimination is just based on how the carbocation reacts with the solvent. So let's take a look at the mechanism in more detail. And the substitution reaction for this tertiary substrate in this alcohol solvent like ethanol proceeds through this two-step or SN1 at a time mechanism. Let's check it out. First step is the loss of leaving group. And something that I'm going to show you in a few minutes is that this step is what we call the RDS. It is the rate determining step. It is the step that basically governs the rate of the reaction. How long will the reaction take, right? We know that the rate law says that rate is equal to the rate constant multiplied by the concentration of the substrate only. And so it stands to reason that if it only depends on the concentration of this, that this first step, the loss of leaving group, is going to be a rate determining step. It has the highest activation energy. Then, if we have the substitution reaction, our alcoholic solvent, ethanol, can come in and act as a nucleophile. We form an oxonium ion, and that undergoes a proton transfer to form our ether, right? You see, we're actually ending up with an ether in the end. And we have a cool name for this reaction. We call this solvolysis. The reason we call it solvolysis is because the nucleophile also happens to be the solvent, right? In this case, it's ethanol. It could be methanol. It could be water, depending on the situation. Now, if you look at the reaction coordinate diagram for this reaction, what did I tell you? I told you that the first step is the rate determining step, and you see that exemplified in this reaction coordinate diagram. Here is the very first step. I'll put a box around it like this. This is the first step, like this, okay? The rate determining step. Why? Because it has the highest activation energy out of any other step. Once you form the carbocation intermediate, you have a really small activation energy for the nucleophilic attack and then the proton transfer. So let's see here. The formation of that carbocation is the rate determining step. And then after the proton transfer, you end up with your final product, your ether. This is just rehashing what I've already told you. The S stands for substitution, the N stands for nucleophilic, and the 1 stands for unimolecular, or you can think of it as being one at a time. It's a rate law that depends only on the concentration of the substrate. You don't have to worry about the concentration of anything else. Now, if you look at a general mechanism for an SN1 reaction, what you're always going to see in common in any SN1 reaction are the loss of the leaving group and the nucleophilic attack. Now, there might be a proton transfer depending on the species that's doing the nucleophilic attack. However, it's always these steps, SN1 at a time. Step 1, loss of leaving group. Step 2, nucleophilic attack. Again, there may be a proton transfer in there, but that depends. Okay, it says there's a proton transfer when you have a neutral nucleophile, okay, because you're going to end up with something with a positive charge. And we'll see many examples of that, but this is the commonality of all SN1 reactions. A loss of a leaving group, the rate determining step, we'll put that here as well, rate determining step, followed by the nucleophilic attack. Well, let's move on from there and let's talk about the E1. If you're wondering, where the heck did this elimination product come from? Same thing. The rate determining step is that loss of leaving group to form the carbocation. And then we can just abstract a beta proton with our solvent to end up forming the elimination product. And of course, you would also form a molecule of the protonated form of ethanol like that. Anyhow, so the ethanol is serving as a base instead of a nucleophile. And just like the SN1 reaction, the E1 reaction is unimolecular. It follows the exact same kinetics. The rate law depends only on the concentration of the substrate. It's the same old, I'll even write it in here so that you can go back to the video if you need to. Rate is equal to K multiplied by just the concentration of the substrate only. Now let's examine the reaction coordinate diagram where we compare the SN1 and the E1, and again, the same old thing. Whether it's an SN1 or an E1 reaction, the rate determining step is that loss of leaving group, the formation of the carbocation. Then the carbocation can either undergo substitution, give you the SN1 product, or elimination to give you the E1 product. Now, if you look at the activation energies for the elimination reaction and the substitution reaction, you see their activation energies are pretty close, right? They're very close activation energies. And here they've shown that the SN1 product is more stable. That is sometimes the case, but not always. Sometimes the E1 product can be more stable than the SN1. It's usually if it's tri-substituted or tetra-substituted. So again, we have our rate law here. E1, elimination, one at a time, or unimolecular, or a first order reaction. Here we go, E1 kinetics. Well, you remember carbocations? We talked about those quite a bit in chapter 2, and we said, hey, if you have a carbocation that can undergo rearrangement to form a more stable carbocation, it's going to happen. And since the rate determining step of an E1 or an SN1 is the formation of a carbocation, you can imagine that if you can form a carbocation, it can undergo rearrangement, which complicates things. But as an organic chemistry students, it's something that we have to be aware of. So let's check this out. The first step, you have this secondary alkyl halide. It's not going to undergo SN2. It's not going to undergo an SN2 reaction. You don't have a strong base. It's not going to undergo an E2 reaction. And so this is going to undergo SN1 or E1. The first step is going to be the loss of leaving group, and we end up forming this intermediate. Okay, so we have this secondary carbocation. Now, if the nucleophile comes in, attacks, we do a proton transfer, we end up with this SN1 product. However, you probably realized right away that this carbocation can undergo a hydride shift, can it? Right, if that carbocation undergoes a hydride shift, and I'm kind of running out of space here, but I'll scribble it in up here, okay? I'll redraw the secondary carbocation, but this hydrogen can shift over here, and then we end up with a new carbocation. We end up with a tertiary carbocation, and that's going to give us this product after nucleophilic attack and proton transfer. And again, since we end up with 1, 2 different carbocations, we end up with 1, 2 different SN1 products. Just the plain SN1 product, if you will, and the one that is formed on account of the 1,2 hydride shift. Same thing down here with this one. If the first step is your loss of leaving group, you end up forming this carbocation. So let's pencil that in. Okay, and if that undergoes nucleophilic attack, proton transfer, we get this product. However, this one can undergo a methyl shift like this to give us this carbocation, so right here, and then that can undergo a nucleophilic attack and a proton transfer to form a second substitution product. And I haven't even mentioned the elimination products yet. Right? We can form mixtures of SN1 products, and then we can also form elimination products. So there's a whole bunch of different products that you can form in SN1 reactions. And you might be thinking, well, jeepers, if you can end up with so many different things, how is this even synthetically useful? I thought you were always trying to take a molecule and get one product, try to limit the side products. Well, we do have to study SN1 and E1 reactions because there are synthetic utilities for these types of reactions. We'll look at them even more today. So when a primary substrate is reacted under solvolysis conditions, only the product resulting from the rearrangement is observed. Check this out. This is a really interesting kind of, I wouldn't call it an exception because it's not an exception. I would just say SN1 of a primary substrate, right? You think about, there's no way, if this is a primary alkyl halide, you might be thinking, well, that's just going to undergo an SN2. But remember, in order for that to happen, you have to have a strong nucleophile, and we have a weak nucleophile. So it's not going to attack the bromine. And if you're thinking, well, I can't just do that. I can't have a loss of leaving group just like that, because that would give me a primary carbocation. That is not going to happen. And so what happens in this case is you wouldn't get any of this product. You would get none of this because that leaving group can't just leave. What you end up with is a loss of leaving group and a methyl shift occurring simultaneously. Whoa, Nelly, that is kind of interesting. Check this out. Something we've never seen until just now. You have the loss of leaving group, right? The loss of the leaving group, the bromide, but you can't form a primary carbocation. And so you get the methyl shift, right? You get this rearrangement occurring simultaneously so that you end up with a tertiary carbocation, and then it undergoes a proton transfer to give you this alcohol. So again, I wouldn't call that an exception, but I would just say a primary substrate can undergo an SN1 and an E1 reaction if it can undergo a rearrangement simultaneously. This is just kind of one of those things that you need to know. And you'll find this in this class in organic chemistry too, that sometimes I'll teach you something, I'll run over, all these concepts, and then they'll just kind of be like one little thing, that you got to know that's sort of put on top of it. It's a situation that you might have to be aware of, that you might have to look out for. And I would say that that's one of those situations. So